No.
question is that?
Will we be getting our test back on Monday?
All right, so I have your test graded. I just forgot to write the grade on there. So I have them recorded in my spreadsheet. So if you would like your test back today,
Yay.
if you don't care about what the grade is, I can just hand it back to you. If you do want to know what the letter grade is, then just give me a couple minutes after class to write it down.
Okay.
Otherwise, you'll get it back on Monday.
So you know the grade, so if we wanna know our grade, you said what?
So I have the test, it's all marked up. I don't have the raw scores at the top or the letter grade, but I have those. I've done that already. I just didn't write it on the test.
So I can just harass you back to the office after class?
Yes.
Okay.
Okay. I don't like the grade.
Or if really you don't care about the grade, I can just hand it back to you.
I care about the grade.
Yeah, me too.
I wanna know how it did.
And as typical, it was a mix.
Was it better than last test? In as far as the base things?
It's about the same. All right, any other questions?
This is the last test that we can have test questions on, right?
Yes.
Pressure's on.
All right, so we were doing energy. How far did we get?
Impulse. We started defining it as the change in momentum is equal to force times change in time.
Oh, we got as far as moving.
Well, it's just a definition of it.
Okay, so we finished energy. Cool. I just want to make sure I didn't. No.
Oh.
Previous.
We talked about the 3 different ways to solve
Okay. Since we have finished the energy stuff,
it. Wait.
let us have. Let's test 1A corrections. Master set 7. Do on the 7th.
Okay. And that's the last one?
No, wait, no, today's the 26th.
Oh, no.
Oh,
Are you-
Master set 7 due on the 3rd.
With test corrections?
Yeah.
The stress is on.
What I would like you to do, feel free to use your notes. I'm gonna put up 2 problems on the board and I want you to work them. Or it would be helpful for me to do one first and then have you do it.
You do one first.
Whichever one.
Okay. Right, getting stuck in the same numbers here, so try some big ones. 2 meters per second. And then 5 kilograms going, I had to go at it at 3 meters per second. First, let's do the perfectly inelastic collision problem, and then we'll do a perfectly elastic. When I say perfectly inelastic, what do I mean?
They just stick together afterwards.
Okay. So we're gonna have a maximum amount of kinetic energy lost. So it is a collision. So immediately what pops into your head is
Wait, what?
in a physics class, if there's a collision problem, what immediately pops into your head? Let me rephrase that. What should pop into your head?
Can I again?
Conservation of energy?
Conservation of momentum.
That's the one.
Oh.
Conservation energy is not necessarily conserved, especially in this one. All right, so we have a conservation of momentum, which means I need to figure out what the momentum is. So what is my total initial momentum? Or let's do it part by part. What's the momentum of my 9 kilogram mass?
18.
Say it again.
Well, not 18 kilograms times meters over seconds.
How'd you get that?
9 kilograms times 2 meters per second.
Or in general?
Mass times velocity.
Yes,
Is it velocity or speed?
velocity. This is a vector quantity. It has the advantage over energy in the fact that we don't lose information, we don't lose direction information. The disadvantage is we're dealing with vectors. All right, what's the momentum of the 5?
Negative 15 kilograms times meters divided by seconds.
All right, the important thing is that they are of opposite signs because their velocities are in opposite directions. Even though it was not stated explicitly, when Robin said 18, he was establishing to the right as positive. So to the right is positive because Robin implied so. Oh, so what's my total initial momentum?
3 kilogram meters per second.
So P, initial, 3, vector, kilogram meters per second. All right. After they collide, what is my final total momentum?
0. My conservation is 3.
Therefore,
Therefore, it's still 3.
yes. So there's my final also. Let's just go ahead and formalize that. Put down the P final. And that's got to be equal to mass times velocity. I have only one object after the collision because they merge. So P final, 3 kilogram meters per second, got to be equal to my final mass, 14 kilograms, times my final velocity.
What are we looking for again?
Final velocity.
Okay.
How is the initial 3? How did we establish?
We figure out what the momentum is of each individual part and just add them. So 18 plus negative 15 is 3. So total is just the sum.
And that's gonna be initial and final because it's conserved.
Yes, exactly. All right, doing the fancy math here, we got 3, the math problem is 3 equals 14v. That's the math problem we're working with. So my final velocity is whatever 3/14 is. Units.
Meters per second.
It's positive, which means that after they collide, they would travel in the positive direction, which is to the right. Perfectly inelastic collision. Are we ready for the perfectly elastic?
So you said the P initial is constant because it is being conserved, right?
Yes.
So what would be an example when it's not being conserved?
When it's basically conserved in what's called a closed system. So I have 2 objects here, I don't have any outside influence acting on it. So if I'm taking into account everything that's of any influence here at all, it's a closed system, momentum is conserved. It would be an open system if all I did was look at just this, because there is an outside influence coming from that. So an example of an open system is, I have a marker right here, I let go, its momentum changed as it fell, because it got faster and faster. So if I'm looking at just the marker, it's an open system, momentum's not conserved, because there was another player involved here. Is that sufficient? Other questions? All right, so let's go to the perfectly elastic collision. So it's still collision, momentum is conserved. What else is conserved?
Kinetic energy.
Yes. So we have three techniques. It really doesn't matter which technique to use. Whichever one you like to use, learn it, know it. It'll help you on the test. Which is a really horrible reason for doing it, but it's a reality. Is there a particular method you would like me to do?
Can you do the one where we outline the last one that you showed us?
Okay.
today?
So we start out with, I got my 9 kilogram mass, and I got my 5 kilogram mass. So we'll call I'm gonna call it the lab frame. It's the problem frame. We're on the sidelines and those are the velocities. So this was 2 and -3. I need to get into the zero momentum frame, and I know to get to the zero momentum frame, I need to subtract the velocity of the perfectly inelastic collision. So I'm going to subtract 3/14 from both of them. So this is the shift to the zero momentum frame. This is 25/14, and this is -45/14. If I had a calculator, I would be doing the decimals of it. You don't have to do the fractions. So 14 times 3 is 42, and then additional again. So fine with that one right now. And that's 28/14 minus 3, 5. So this is in the zero momentum frame. Then they collide. Collision. If I'm in the zero momentum frame in a one-dimensional problem, I just change the signs. So this becomes -25/14. And this becomes +45/14. This is still the zero momentum frame. This is before and after. I need to shift back into the lab frame, into the problem frame. So +3/14, +3/14. Because when I shift back, I just do the opposite of what I did before. I got out of my lab frame by subtracting 3/14. I now shift back in by adding 3/14. And so I end up with -22/14 and 48/14 meters per second. So this is 3 and 6/14, which is 3 and 3/7, which is 3.42 something meters per second. And the other one, 8/14 is 4. The other one is -1 and 0.57. I think. Ish. Questions about this technique? This is the third one.
So to get to the perfectly elastic, we have to go through the perfectly inelastic first so that we can find the collision.
It's helpful, yeah. To me, that's the simplest. All right. Is there a desire for me to do one of the other techniques? I'll take that as a no. As one person expressed an opinion, and it was a handshake. All right, so what I would like you to do, why don't I give you one where the numbers turn out as integers, or at least nice numbers, if not integers. I've done that one already. This one, there we go. All right, so what I'd like you to do, as you're sitting right there, live, is we will have a 4 kilogram mass heading to the right at 10 meters per second. It is in pursuit of an 8 kilogram mass heading to the right at 1 meter per second. There's a perfectly elastic collision. What are the final velocities? V4F and V8. And let's make sure I didn't get any numbers backwards here before we. Oh, that should work. And because I have plenty of video of silence and nothing happening on camera, why don't I pause this? Pause that? Oh, actually, let's stop that.